So now let's talk about equilibrium at partial pressure. So previously, we were talking about the melting and freezing of water. Now we're going to talk about evaporation and condensation. Now, in a single component system, let's just say a glass of water, the vapor and liquid of H2O are at equilibrium. The equilibrium vapor pressure of the material is defined as the total pressure generated on the material by the vapor, and we call that PE. We can change the amount of pressure by the vapor on the water, for instance, by introducing an inert gas. So let's take a look at this diagram. Let's call the total vapor pressure PT. That is the total amount of pressure that's being exerted onto the liquid or the water. In normal circumstances, without an inert gas, the total pressure would be the pressure of the ambient water vapor. However, if we were to introduce an inert gas, let's just call this PI. The total vapor pressure, PT, will be equal to P plus PI. And P is no longer just the ambient vapor pressure, but we now refer to this as partial pressure. So let's see how we can calculate the change in Gibbs free energy during condensation and evaporation. Let's allow PE to be the equilibrium pressure, PT the total pressure in the liquid, and P the partial pressure. Taking this formula, this very familiar formula by now, dG is equals to V dP minus S dt, we can express the change in Gibbs free energy for the liquid as this equation. And since we're holding it at a constant temperature, we can cancel off this term because dt is equals to 0. Hence, total change in G liquid, which is delta G liquid, is equivalent to the molar volume of the liquid multiplied by the total pressure minus its equilibrium pressure. So, assuming an ideal gas, the Gibbs free energy of the gas must also change. We can then substitute the ideal gas formulas to simplify to RT d ln P. Why ln P? Because dP over P is equals to ln P. And that leads us to this final expression where the total change in Gibbs free energy of the vapor is equals to RT ln P over PE. And now we've established a new equilibrium. As a result of establishing a new equilibrium, we can ignore PE. And so what we want to do now is to equate the total change in Gibbs free energy for the liquid to the total change in Gibbs free energy for the vapor. Since PT is very close to PE, we don't really need to integrate, and so eventually we will end up with this final expression, which equates the change in Gibbs free energy of the liquid to the Gibbs free energy of the vapor.